Hello and welcome all of you to the keynote talk of today. We are very fortunate to have somebody who is a leader in an important area, which is the AI and its applications to actual real world problem. Let me introduce our speaker. The speaker is Dr. Ruchi Puri. He's a chief scientist of IBM Research, an IBM Fellow, and vice president of IBM Technical Community. He led IBM Watson as his chief technical officer and chief architect from 2016 to 2019. And I'm sure you all have heard about IBM Watson and the important research which has been done. He has held various technical research and engineering leadership roles across IBM research business. Dr. Puri is a fellow of the IEEE, has been an ACM distinguished speaker, an ACM distinguished lecturer, and was awarded the 2014 Asian American Engineer of the Year. Ruchi has also been an adjunct professor at Columbia University in New York and a visiting scientist at Stanford University. He was honored by the John von Neumann Chair at the Institute of Discrete Mathematics at Bonn University in Germany. He's a prolific inventor. He has over 70 patents in the US and has authored over 100 scientific publications on very important topics, including software and hardware automation method, microprocessor design, and optimization algorithm. He's the chair of the AAA conference, which focuses on industrial application of AI. He's really a thought leader. His technical opinion are really important and has been widely featured across the media, including New York Times, Wall Street Journal, Forbes, Fortune, IEEE Spectrum, among others. So at this point, I could say much more, but we really, I'm sure, are all eager to hear his presentation. So I leave the floor to Ruchi.
Thank you, Alyssa. I really appreciate the kind words and the kind introduction. So today I'm going to talk about an important topic I know will be near and dear to you all. We've been hearing about AI for long, so this is not a new word, at least not in recent history. But I'm going to talk about the scaling of AI for the enterprises. So let me just share my presentation. And okay. Okay. So as I said, we've been on this journey for a little while, but also as we see this from an industrial perspective, we just went through an era of what I will describe as 1,000 flowers blooming. What do I mean by 1,000 flowers blooming? Which is a lot of data scientists in industries, academia, researchers. They've been coming up with lots of methods. But it takes something more than scientific research to really push the frontiers of enterprise applications. So what does it take to scale AI for the enterprise applications is what I'll discuss today, and how we can do this as a community a lot better. So if you really look at AI itself, I would say data science as a discipline is a combination of multiple skills. Obviously, it incorporates mathematics and statistics, and computer science and coding as well. But just the overlap of those two, mathematics and statistics and computer science, is actually machine learning. If you look at the overlap of the skills between computer science and coding and domain knowledge, that actually is application software. And if you look at the overlap of domain knowledge and mathematics and statistics, that I would describe as sort of traditional operations research. And the combination of all of these three, which is machine learning, application software, and traditional research, is where the discipline of data science meets industry. So I think one of the things that we've been looking at is, since it is such an interdisciplinary area of computer science, of mathematics and statistics, and of domain knowledge, which is interestingly one of the foundations of how applications and the industry meets AI. Now, short of scaling the training of individual in all three dimensions, good data science as a skill for industry is hard to scale because it actually involves domain knowledge, and domain knowledge is not easily scalable. The only viable solution is to replace one or more of these quadrants with automation, and that's what we will talk about today, among other things. And automating, as I said earlier, automating true domain knowledge is one of the hardest of these three buckets of computer science, domain knowledge, and mathematics and statistics. So industry domain is where eventual realization of AI value add happens. But we will talk a lot more about how can we scale AI better by automate how we build AI-infused applications, how we deploy AI-infused applications, how we automate algorithms, and how we automate the coding parts of it as well. So let's step back and look at, obviously, this is a little bit dated actually chart, but I deliberately picked this one because it actually gives an indication of what happens 3 years back. And obviously, demand of AI skills has gone through the roof. This is 3 years back, and the situation has only worsened recently because the chart that you see on the left-hand side, which is on AI skills, are quickly spreading beyond just the technology industry to every industry, actually. And you see this in the LinkedIn post because every industry, whether it is in retail, whether it is in finance, whether it is in manufacturing, whether it is in healthcare, and entertainment and beyond, all are looking for AI skills. And if you look at just the job reportings and categories, machine learning engineer as a job category grew by 12x in 2018, and that has been actually, that pace has only picked up. So that's the demand side of the equation. Let's look at the supply side of the equation. Obviously, if you look at the supply of AI skills, the need for those skills and the hardness to meet that demand, actually, how hard it is to get those skills. So here I'm showing a plot of hardness to fill a particular role and the projected growth of that particular role as well. And the disruptors are in the upper right-hand quadrant. And most of the things that you see in the upper right-hand quadrant are the skills around data science, machine learning, data visualization, big data, R, data engineering. So all of these related to AI are the ones which are in disruptor category. So their projected growth is highest. However, they are hardest to fill as well. And therein lies the problem. We have a problem at hand because we really want it and we can't get much of it as well. So if you look at that, I'm trying to build a case for automation actually of AI to scale AI. And if you look at case for AI automation, if you look at the workflow of AI, it's much bigger and lot more complex than just algorithms that we tend to love and work so dearly on. It starts really with data. At IBM we call it the ladder to AI. There are many rungs of that ladder, and obviously it starts with data, ground truth gathering, data cleansing, feature engineering, model selection, parameter optimization, ensemble building, model validation, deployment, monitoring, and a continuous improvement. And that cycle keeps on going. But a significant effort on getting of that entire life cycle is spent on getting data ready for AI. And that's what we will talk about in significantly more detail as well. we have noticed another thing actually, which is since we are giving, we are collected together in a forum of services conference. I'll also talk about services. We have noticed in many cases that AI companies, in particular startups, and otherwise too, simply don't have the same economic construction as a software business. It may appear like a software business, interestingly, but at times it can behave much more like a traditional services company. And I'll elaborate a lot more on this. And there's a wonderful report written by Anderson Horowitz, the VC company, on this particular topic, on what are the similarities between an AI business and a services business. And I'll pick some quotes from this report to illustrate the point, and then I'll expand on that a lot more. So if we compare software versus the AI-driven business, in many cases, AI companies simply just don't have the same economic construction as a software business. As I said, they at times they will look like a services company, and the artifacts of those are, and the symptoms of those are, the companies have lower gross margins due to much heavier cloud infrastructure usage. For anybody who is use it, the other day I was trying to use that Google Colab, and I just spun a book and I was training a model, and for 2 days of usage I ended up getting $100 bill actually. So GPU usage is a significant infrastructure usage is a significant cost of those sort of reduction of those margins, because these resources are expensive, and models are just continue to get larger and larger in their complexity and take longer time to train as well. In addition, we also face what we call scaling challenges due to tough problems of edge cases. AI model works in most of the cases, but it doesn't work here. So I need to do something special over here. And then, there is another corner case, I need to do something special over there. And it really encounters some of these scaling challenges as well. And the other one is, I think this is one of the only fields I have seen which is commoditizing. The research is really done in open, truly in open. So this is all about open innovation. People publish amazingly fast, and they are, that actually gives rise to weaker, what we call defense moats, in terms of the defenses of the company, in terms of their IP, because a lot of this is, kind of is in open and is commoditizing fast as well, which is wonderful for the community and wonderful for making progress, but it makes it harder for the businesses. So we have seen surprisingly consistent pattern in the financial data with the gross margins often in 50 to 60% range for AI companies, which is well below a comparable, a sort of a equivalent, if I say a comparison benchmark of SaaS businesses, which is many times 80% plus margins. So that appears, interestingly, more towards the services business, or somewhere between a services and a SaaS business, which is a software business, truly a software business, versus a touch-heavy services business. And early stage private capital obviously can hide these inefficiencies, because you see too much of money, a lot of money pouring into this to really push for adoption of AI. But any amount of long-term product or market optimization can completely solve the issue. But this is what we will talk about regarding how do we actually sort of increase the margins in a AI business, and how can we make it less like a touch-heavy services business and more like a software business as well. So as I just laid out, AI business is not a software business only, because of various challenges that I just pointed out. It's more like a software and a services business together, which makes for an AI business. And that's the point we will debate today, and give, how can I reduce more on the touch-heavy services and increase the software side, so that AI business becomes a lot more profitable. So all companies appear, the AI companies increasingly combine elements of both software and services due to scaling, due to corner cases, due to data heavy lifting, and so on as well. And users can and they will enter just about anything in an AI app, by the way, because they expect it to work just like you say, hey, AI is like it's intelligent, so I could just enter anything, and if it is not okay, it should be able to just discard it. So they have an expectation. Think of it from an experience point of view. When we say, and we are doing ourselves sometimes a disservice, when we say artificial intelligence, it actually is implying there is real intelligence, and it's really trying to mimic artificially that intelligent. And we are further away from that kind of robustness. And given that sort of notion, and users expect that to be true, so they will enter whatever they can, or just like they will do for a normal human being, give the data, any data, and they should be able to reject it. So the need for human intervention will likely decline as the performance of AI model improves. But it's a journey we are on. We are not all there yet. There are lots of corner cases. You have seen this in facial recognition. The data can be biased. There are many other issues that up. And it's unlikely, though, that humans will be cut out of the loop entirely. Because, just first of all, we need to govern this. Second, the corner cases will always continue to exist. And I truly believe AI will be deployed in practice with human in the loop. So there will always remain a component of some of that services aspect, if I may, because there's a touch related to it as well. So if I look at the AI lifecycle, on the left are the AI models, on the right are AI applications. Those are traditional. That's on the left is the AI model lifecycle. On the right is software lifecycle. Interestingly, if you look at these two as gears, they may not be at the same frequency, and they can actually collide and make the movement with lot of friction, and sometimes they can sort of log jam as well. What do I mean by that? So let's look at, I already talked about the AI model life cycle. On the software life cycle, you basically go through services adoption, dev stage, production environments, continuous integration, sort of the CI/CD pipeline, regression testing, A/B testing with experiments, canary testing with canary deployments, runtime monitoring, and that cycle keeps on going. Actually, you get more feature function, you adapt, you do dev, stage, prod, you do CI/CD, and so on. Actually, but these two cycles need to actually work together well. So on the left hand side, if I look at some of the characteristics of that life cycle, it is characterized by ad hoc processes, long running stages, high degree. Why do I say long running stages? Collecting data, cleaning data takes time. Obviously training models can take time as well. Whereas, so there is high degrees of manual involvement in the AI models, and that takes time. Lack of scalability and repeatability is an issue that could take time, and low change frequency. You don't change your model, every day. Actually, on the right hand side, it's a well-defined and a mature process for a software application. Traceability, repeatability, and auditability is taken for granted, whereas repeatability is harder on the AI models. High degrees of automation, because on the left-hand side, it is statistical. On the right-hand side, it's deterministic. There is high degree of automation in that life cycle, and there is continuous delivery, as I talked about CI/CD. So the frequency of these two motions, of these two cycles, is actually can be at a very different speed. And they actually can get in the way of each other because the AI model, like for example, an application, software application, users and the developers may expect it to be changed multiple times a day. Actually, in a cloud native application will change multiple times a day. And it's all seamless, it's all automated. Whereas if AI model was part of it and they expect the AI model to change as well, that can't happen. And this, how do we actually make those two cycles work together, is one of the key things that we will discuss. So scaling the end-to-end AI lifecycle is a critical part, and there are, I would say, three major stages of it. The first part is the data science lifecycle, and the second part is the deployment and the operations lifecycle of an overall AI application, which involves data preparation to modeling, which is about really AI modeling, which includes feature creation, modeling, training the model, and quality assurance. I think I want to make sure we focus on quality. Quality is critical to any practical deployment in industry and any practical application. And then finally, AI operations, from a test and validate to deploy, monitor, analyze, recommend, and improve. And then continuously that life cycle goes on. Really, we need to define agile end-to-end life cycle processes to deliver this continuous improving model versions, provide accountability. It's critical. I think if AI is ever going to be widely successful in practice, it needs to have accountability. The trust of AI is critical to what we do, what we focus on at IBM. And I think industries and academia is obviously adapting more and more in terms of this being a major topic that we focus on. Auditability and full visibility into all aspects of that life cycle drive high degree of automation, integrate human in the loop life cycle aspects wherever possible, wherever critical decisions are being made, to make it practically feasible. So let's, I would not talk a lot about the data science lifecycle part of it, because a lot has been written on it, a lot has been said on it. I'm going to talk about where rubber meets the road, which is about taking AI to production in business critical applications. Building a model is only the first step. What we must consider is validation of that model, safe deployment, monitoring, maintenance, and continuous improvement. So if at IBM, we have been developing a toolkit. We call it the AI Operations Lifecycle Toolkit, to obviously focus on the entire AI lifecycle, focusing a lot more on several of the toolkits that are described in the sort of the bluish green color below, which is a performance prediction toolkit. So pre-deployment, we need to do a test on how will this model perform in production. We have a toolkit for reinforcement learning, which can be actually about when we deploy it, how do we learn as well as part of that deployment. We have drift detection toolkit, which enables us to monitor the model and monitor if the model is drifting from its original intent, that we should be able to catch. We have KPI Insights toolkit for telling us what impact does it have on your really business metrics. Look at it that way. And then we have a goal-driven active learning toolkit that allows us to improve the model on a regular basis. So these are some of the key ingredients and capabilities that go into making practical deployment of AI-infused applications possible. So I won't go into a lot of detail. I'm happy to send the deck out as well for anybody who's interested. But in terms of pre-deployment test, assessing the performance risk of a new model version is critical. When you test it with the test data, you get a test accuracy of 92%. When the real traffic flows through, the real accuracy is 62%. How do you make sure you actually sort of minimize that difference of when you test it versus when you deploy it in production? So pre-deployment tests should be able to predict model performance on unlabeled production data, evaluate the quality of test sets for the given production environment, and performance test for a specific operational scenario as well. Performance prediction itself, I talked about the performance prediction toolkit. For us, it's a Python library that includes algorithms to train performance prediction models. policies and use cases. Again, policies are critically important, and evaluation utilities. This is really about predicting model performance before deployment, evaluate the quality of the test sets, and make sure the test sets are in line with predicting the quality when the model will be deployed in production. In terms of deployment, it's all about managing the operational risk of new model versions. When is it safe to deploy a model? Using AI for safe deployment version rollout. So we use AI itself for doing safe model version deployment. Learning the best performance version. Think of it as an AI variant of a A/B and a canary testing, and learning the best performance version. How can we do that is what this capability is focused on. We also have, and I won't go through this in detail, some very interesting algorithms that we have worked on for safe deployment with multi-arm bandits, learning to choose the best performing model based on the observed reward. That we have written papers on it as well, and I'm happy to send references to anybody who's interested. From again, keeping the theme of deployment, Lifecycle Toolkit for safe deployment, which is a Python library for us, a contextual and a non-contextual multi-arm bandit algorithm that I just mentioned, again, focused on policies and use cases and evaluation utilities. In terms of monitoring, the challenge is about how to reliably detect model performance. And this is really, the scenario is described here. Day one traffic was you were getting accuracy of 92%, and when as the model continued to be deployed, the accuracy degraded over time. It's about continuous performance monitoring and prediction without manual assessment, detect model drift, alert of performance degradation to the model owner, and then so that intervention can be done in time before the model has had some bad side effects. Again, about performance prediction, it's a Python library for us, and sort of similar scenarios that I mentioned before as well. In terms of analyzing and recommending, the challenge is on understanding performance and the impact on KPIs. KPIs are key predictors and insights. Just for people who may not be aware of the acronyms, it's key predictors and insights. It's about monitoring and analyzing model metrics in the context of the business. It's really about what impact it can have on business. It's fine to tell me what is the F1 score, what is your ROC curve. Those are more, what I'll call geeky data science metrics. What business functions really care about, or business owners really care about, is what impact it'll have on my business. So KPI-driven model insights and improvement recommendations analyze and improve models in the context of the business, as opposed to only isolated, data-intensive or data metrics only with accuracy and thresholds. So connecting model metrics and business metrics, it's the recommendations will be given on identifying the model improvement opportunities that have the potential to improve target API. Again, we have what we call a dashboard. This is sort of because business people interact with it. We have a much more seamless experience in terms of how can we, convey what is a better model to pick in terms of the business impact. Finally, the stage of improvement. The challenge is on how to harvest new training data from logs to improve the performance. And the focus is on goal-driven active learning. So we focus on goal of improving a target business KPI or key predictors and insights. Minimize the log data labeling efforts. This is all done mostly in an unsupervised way. Because if you start labeling the data and what is good and what is not, it becomes very expensive with lot of demand for labor. So we have introduced a lot of automation in it as well. And the active learning is about the importance of data selection. What the cost of labeling data can vary dramatically depending on the goal that you are trying to accomplish and the selection technique used. We've been working on techniques that enable significantly less involvement in terms of manual labor for data readiness. We actually look at production logs, which are unlabeled data. We do active learning on those logs in terms of how we select the data. We do have human in the loop, but minimal effort is required on the human part. And most of it, this is done with querying log data automatically, selecting the right set of data, just selecting one of that data, and then propagating that label to rest of the sort of think of it as clustered data instances as well. In terms of the goal-driven active learning, our goal of the toolkit is to improve precision, expand coverage, improve accuracy of certain classes, more importantly, reduce bias, and improve precision without increasing bias, because you can really drive the model in one direction and improve coverage and finally reduce bias as well at the same time. So that those are some of the goals that we work on when we are at this particular stage. So I think as I went through this, it becomes apparent that there is obviously a significant need for, when AI infused applications are developed, they go through the dev and staging and production pipeline of a software application. They are software applications. AI is part of a broader application. AI is not an application by itself. Again, what I usually say is AI is a means to an end. It's not an end in itself, in industry at least. And as I was talking earlier, I think we were looking at the Venn diagrams of these three circles, and obviously the machine learning skill itself, as we talked about in the very beginning of the discussion, is a very high demand skill and is much harder to find. And I think we have been focused a lot on efforts of automating machine learning and data engineering. That's where a lot of our focus is on, including automated quality assessment of data, automated bias detection, automated drift detection, and so on. And I'll talk now about that in this part of the talk, on how do we go about automating machine learning and data engineering, which is the combination of computer science and coding skills and mathematics and statistics. Because domain knowledge is, I could almost argue, impossible to automate. It's gathered over years of experience. And data science or AI in practice is all about the merger of machine learning and application software and really domain knowledge or as well. And I think what I'm saying is we need to evolve the three circles to pretty much a ellipse, which is a combination of machine learning and data engineering, computer science, and mathematics and statistics, with the auto AI and domain knowledge really fitting into this. So to a large extent, I think data science as a skill will continue to get automated with people who have domain knowledge will differentiate with respect to other who only have algorithmic knowledge. Let me say it this way. And I think that should give us some guidance with respect to when we go in industry. It becomes important for us to not only have a data science hat on, but also a domain knowledge hat that we have it on or we are trying to build, because it's that domain knowledge, it's the merger of that domain knowledge and the data science skills where rubber meets the road. So in terms of automation of AI, we've been focusing on AI, designing AI itself. I'll talk a little bit about that. There's been lots said and written in the literature about this, and AI, optimizing AI as well. So how can AI help design AI? How can we automate designing of AI itself? How can we design better neural network architectures? How can it tune the model for me automatically? And the next one is, how can it optimize that for me in the context I am as well? And finally, it is about how can AI monitor itself and how can AI correct itself? How can it tell me I'm drifting from where I was designed? How can it tell me I'm biased? So it should be able to point these things out to me automatically as well. And obviously, there'll be always a human in the loop where the decisions are truly critical and life and death situations. There will always be human in the loop to make sure we have governance on this as well. So in terms of AI, designing AI, let me just first see quickly how I'm doing on time. I have 20 minutes left, so I'm just gonna wrap in 5 to 7 minutes or so and leave time for questions. So in terms of AI, designing AI, obviously we talked about highly skilled researchers, data scientists are needed to handcraft custom neural networks, build ensemble models, the right ratio of the ensembles, when the ensemble, what part of ensemble kicks in when. It's a handcrafted, complex network, just in terms of designing neural networks themselves, is time consuming, error prone, and does not scale with time and resources. And also, one thing we have seen is neural networks continue to explode in size with GPT-3, with literally we are getting to trillions of parameters. It's I am of the opinion this is getting out of hand, because if I usually am fond of giving this example. If you look at, we are trying to say we are building AI, which is artificial intelligence. Let's then we should benchmark it with real intelligence. Real intelligence, which is most of our brains, is intelligence that can do multitude of tasks seamlessly without even knowing. Actually, it's mind-boggling, no pun intended, how many tasks it can do at the same time without even blinking an eye. And it actually resides in a volume which is 1200 centimeter cube. So this brain of ours has a average human brain size, adult brain size is 1200 centimeter cube, and it actually consumes 20 watts of power and runs on sandwiches. I'll challenge anyone to point me to a equivalent computer or a equivalent artificial intelligence system that actually meets that spec even remotely. I would give 5 orders of magnitude as well related to it. So we are far away from what we are trying to do. So we have to find, this is a little bit of a tangent, but we have to find more efficient, power efficient way of doing what we are doing, which is, that's a talk for another day on future of computing. Which I'm happy to give in a different forum, but that's a fascinating topic in itself. But I think the topic, yes, neural networks are becoming much more adapted by the industry. How do we go about automating them? We at IBM have been working on something called NewNets as part of our Watson Studio capabilities for taking it's a new AI engine for designing neural networks themselves. Google has AutoML. There are other capabilities in industries for what is now called as neural architecture search. I won't dive too much into it, but what capabilities like these do is they generate the optimal neural network for a given training data without much coding required. They optimize the design of the network, the layer selection, the network evaluation, and significantly decrease the time required to build and deliver AI to applications, to infuse them in applications. They allow you to easily tailor the model accuracy, inference time, model size. You have seen these trade-offs. If you go to any of these services available on the web, you will get this trade-off between model accuracy, inference time, and model size. Do you want to deploy this model on the edge, and so on? And it generates models optimized for targeted applications, including, as I said, download to edge devices and enterprise applications. And they've become very compelling, actually. More recently, they've been getting to the point where they are actually sometimes better than human accuracy, or at least even within a couple of decimal, fraction of a percentage point within that accuracy as well. And again, I'm usually, fond of saying this as well, that don't tune your accuracy to 0.01%. It doesn't matter, because you're going to deploy this in practice and you don't know. There's only one golden truth, which is, when this model is deployed in practice. So that's more important than this academic benchmarks of I'm 99.01, so I'm better than you because you are 99.005, actually, as an example. So this is actually just one example of, we're showing the model optimizing itself. This was a model that actually started from 83% accuracy. And this is actually a fast forward of when it is training on GPUs, and it'll end up with something like 93% accuracy or something. But it's really trying to change the model, the layers. It's trying to increase the size of layers and so on as well. And you see on the lower right hand side, the number of layers and the time it is taking for it to optimize. And yeah, it can be a compute intensive process, but you get a lot more of this automatically done as opposed to a lot of human labor. The other one is AI optimizing AI. We all know that the task of feature selection is a hard task. Coming up with features is difficult, time consuming, requires experts' knowledge. What we call applied machine learning is a hard task and is manually intensive. The algorithms we use are very standard for Kaglers. We spend most of our effort in feature engineering. So you really, as data scientists in practice, feature engineering is still a significant part of what they end up doing. And you get original data, you are sitting there, you are trying to see what things I can combine, what mathematical functions I can build on top of data, what is related to what. You're trying to induce your intuition as well as part of it. And outcomes, I think, I had two features of x and y. Maybe I should take log of x and x plus y and x square and frequency of x as some of my features and build a model on top of it. And then you get a transform data, and then you build a model with scikit-learn, Veka, and all kind of stuff actually that you could build this with. And the data science expertise provides the hunch on which transformations to try, perform them iteratively through trial and error, and then finally choose them. And AI optimizing AI is all about how can a machine perform all of this with experience, or capture the experience or expertise, code and trial and error, and automate all of this. And we've been working on this as well as a critical part of it, in the spirit of really minimizing some of the remaining time and focus on the Q&A session. I'm going to skip some of this and focus on this one that we are very proud of actually, which is AI correcting AI. And I'm going to just talk about this and then stop after this. This is really about, think of it this way, when the model is deployed in practice, it actually is making decisions. And it may be making decisions on data where it has drifted from its original kind of domain it was trained on. What do we do in that scenario, actually? What can you do there was a bias detected in the model, assume for the time being. How can we detect the bias automatically, number one? And how can we correct the bias automatically as well? The best analogy I can give for AI correcting AI is following, actually. Now, there are two ways. If I detect a model has something wrong in it, there are two ways of going about it. I'll equate this to someone who is short of far-sighted. Let's say it this way. I actually have trouble seeing far clearly, so I wear these glasses. Now I have two options. If I detect if I was a machine learning model and I detect I have a problem, which is my eyesight is not that strong, and I have two ways of going about fixing it. I could actually get what I call laser eye surgery. It's available. It's a commodity. I could go and do that, which is equivalent to saying, you data scientists go fix this model. And it takes a long time for them to fix it. The other one is I could actually wear glasses, which is think of it as a surrogate model, which sits on top of the original model, which is me. The original model is me. And it sits on top of me and is able to correct the bias which was there in my original model or defect in my original model. We have built this equivalent of this particular notion of surrogate models, which sit on top of the original model and are able to observe things and are able to correct things automatically as well. You can certainly go on Google Scholar, search my name, and you will find papers on it as well. But again, one of the key things we are very proud of, and this was built as part of a product that I think one of the products I'm most proud of building actually was this one. You can also Google it. You will find enough literature on Watson OpenScale, now part of our Watson Studio Trust capabilities. So I'm going to just stop there and leave time for question and answer, roughly 10 minutes remaining. And Alyssa, I'm going to hand it back to you.
Okay. Oh, thank you for the very exciting and inspiring talk. So for the audience, please write your questions in the chat. Okay, so I suggest while we wait for questions, I have a lot of questions, but I'll start with one, okay? So it's very clear from your presentation that at the end of the day, an AI artifact is a combination of some algorithm with the data, because at the end, the model is, let's say, a neural network trained with certain weights obtained from the data. So at this point, and especially now, whether you will have even AI being able to design other AI, to whom the intellectual property belongs to? Would this be a model belonging to IBM or to the company for whom IBM has designed this model, to both?
That's certainly a very interesting question, and this truly goes to, it's an evolving area. But on that particular one, I would say the tool to design AI model is a tool. I'll give actually equivalent of this in other industries. Take chip design industry, which is a lot in news these days. Actually, we are going through a global supply chain which is having hiccups on semiconductor, whereby really stopping a lot of production in several industries. There are lots of tools for designing chips available. There are companies who sells these tools as well, software tools actually, because the chip design process itself is a software design in itself. Actually, they're not designed by hand; they're designed by tools. Who owns these chip designs? Well, it's the company who designs these chips. It's not the companies who provide the tools that own them. It's the companies that design these chips, because lot goes into that chip design process. It's the data of the company. So to me, again, there is that equivalent should carry over, which is to a large extent, AI models are a representation of data in itself, some kind of transformation on that. You compress it, you build features out of it, whatever it might be. It's the data in itself which is represented in that AI model. So who owns that particular model is the person, the enterprise, the entity who designed that model. Now, I think it becomes little bit trickier regarding if there was something wrong in it, whose fault is it, and who is going to govern it. And again, I think if whoever designs the model has also the burden of making sure that it's not biased, because to a large extent, obviously, there are two ingredients that go into it. The algorithm itself could be biased, or the data could be biased. And to a large extent, it is the task of the model developer, who, or even the business application owner who deploys that model, to make sure it doesn't have the bias, and also to make sure it has proper monitoring built in, which is what I focused a lot on, because it's almost impossible to design a perfect model. Yeah. You need to make sure of that monitoring as well. So I'm just going to stop there and see if it addressed your question.
Yeah, in part, but for example, recently, I think somewhere in Australia, some law court even said that an AI algorithm, let's say AI, can be the holder of a patent, right?
Yeah,
which to me seemed a bit strange, because I don't know, somebody designed that AI algorithm model. So.
Yeah, I think it's an evolving area, and again, I think I'm sure academics who are at the intersection of law and IP law and algorithms will get their say into this as well. It's my personal opinion that seems stretched. I would agree with you, Alyssa, on this, but I'll have the lawyers have their say as well, actually. So
yeah, I know, but. Yeah, so let's see if the audience has questions. Please ask, because I don't see anything in the chat unless I do something. Do you see anything in your chat?
I think the one I'm seeing is a private chat, so I'm not very sure if
Exactly.
there is
Okay. Oh,
okay,
there are no
someone.
questions from the audience. Okay, so I can continue. I'm sorry to keep asking questions, but you pointed out a very important problem that is correcting AI. So in that case, you needed to do a precise diagnosis, being able to know whether it's the problem of the data or the problem of the algorithm, but or biases in particular. So, but how can my impression is that in general biases come from data, but according to what you say, biases come not only from the data but from other sources. So what would that be exactly?
So I think that's I think you're pointing out something very important, which is once I detect a bias, and I have a complete video on it as well, and I ran a short of time, so I wasn't able to show that in the end. But once I detect a bias, so first of all, how do I know I'm biased? Let's start with that. Obviously, a human needs to tell me this is acceptable and this is not acceptable. Let's take even, bias is also subjective as well. Certain norms are acceptable in certain societies, they're not acceptable in certain societies. So it's very cultural. Bias itself can be very cultural. So first of all, how do you define bias? It needs to be defined by the users themselves or by the consumers of that AI. That's the first one, and we have mechanisms in the product for users to be able to define what is bias, what are acceptable bounds of your. Second one, once I detect a bias, then I think what we are doing is we collect we collect that particular data instances on which I detect a bias. Um, since I know it is biased, I also know what should the correct answer be as well, by the way. So what I do is, or what we do is, we siphon those inference instances or that part of the data into a side bucket. And once I collect enough of that side bucket, we train on the fly a corrective model, actually, because then I can think of it as the outputs from the original model are coming biased. I have an anti-bias model which is sitting at the output and modulating the output as well. And this happens not right away when I detect a bias, but over time when I'm detecting that bias, collecting enough data to train this anti-bias model. And I'm happy to send link to you, actually, which on the side that demonstrate this in a very nice visual way.
Okay, yeah, I have some more questions, but there is a question from the audience. Perhaps you can read the question directly, and if you can repeat for the audience.
I would. So the question is from Kinichi Takasaki. Is data more and more important than AI itself as AI automation technologies go on? Excellent question. So interestingly, our esteemed Professor Andrew Ang has also been on this topic, and I really believe, actually, I think data has tremendous influence on AI. I would argue even more influence on AI than algorithms itself. And in fact, a lot of the competitions that you see, academic competitions, Kaggle and others, they fix data and they ask you to come up with the best possible algorithm. I think many of the people have been on this point now that we should fix the algorithm. So you can only use this algorithm, transform the data any way you like. Here is the data given to you. You can transform it any way you like. And then, tell me what is the best possible you can do. And I believe for practical deployment of AI, yes, data is more important than AI algorithms themselves. In no way I'm minimizing the importance of AI algorithms. Tremendous. I think every once in a while, a step function comes about, whether it is in NLP, BERT models, or GPT models, or transformers or other concepts come about. But to a large extent, on a day-to-day practical applications, data has a lot more influence on it. So in summary, I will answer, Kenichi, to your question. Yes, data is more important. And specifically, as AI automation becomes more and more automated, as AI building becomes more and more automated, data actually becomes more and more important because rest of it is automated from a practical execution point of view. Very good question.
There is another question.
So from Adib Ridiman, when an AI model is tuning or designing another AI, how are they held responsible for any controversial actions, especially since there is no human in the middle? Okay, this is another very good question, and I think we can be here for long actually discussing these. So I would really say, when it is designing the models, yes, there is no quote unquote oversight on it, but the oversight is really on the results of that model and deployment of that model. So it doesn't matter how that model was designed. We need to make sure that model, before it is deployed in practice and while it is deployed in practice, is continuously monitored. So I think these are the important aspects that I try to lay out, that it's not even sufficient to say, I tested my model on this test data and it's good. Like, well, how do you know it will remain to be good 20 days from now, 1 year from now? So that continuous monitoring part and identification of that bias, detection of drift automatically, all of that is critical. So Adib, you are right that who is held responsible? Finally, it is the business and responsible for the decisions made, and that actually requires certain steps in terms of tooling for software and AI lifecycle, the ones that I took through. So I hope I addressed your question, because there is a human in the loop in that entire lifecycle. Absolutely, there is a human in the loop, but just in the model designing itself, there is not. But the output of that model designing, there is a human in the loop actually. The next question is from Jia Chen Ma. Do we need a stronger bias for AI to learn on small data sets compared with large data sets? Excellent question again as well. And again, I have a different talk on learning from little data versus learning from from big data. And I think there needs to be a balance. But one thing that I point out in that talk is that in industry, data labeling is a massive problem. There are tasks, obviously, leave aside NLP, but when I'm trying to do a particular task, I go to I'll give you a concrete example. Let's say, risk of a particular financial instrument. So a bank or a financial institution is trying to build a model which is trying to determine the risk of certain financial instruments. Now, there is maybe 2 or 3 groups in the entire bank who really know this in detail. So this is where subject matter expertise comes in. Now, by the way, they have a day job. So they're not going to just leave everything they're doing and just design, help you design the model, because they have a day job. Bank is functioning on an everyday basis. So maybe they'll give you part of their time, actually. Say, okay, I'll give you 10% of my time to guide you on how to label this data, which makes this process extremely slow. And also, they don't have a lot of interest in, this is human part comes in. They don't have a lot of interest in replacing themselves totally. So they, this part of human aspects come into this as well. And thereby, we have to come up with better techniques that learn from little data versus, this big data, because by definition, we are limited in terms of how much of data we can get for many practical contexts and many practical use cases. And I think academia has progressed a lot more on this recently, but a lot more needs to be done in this area. Again, drop me a note. I'm happy to discuss this more with you. So Alyssa, I'll send it back to you.
Yeah, okay. We have time actually, so there is a time for more questions. But I wanted to follow up one of your reply, the reply you give to Kenichi about whether data is more important than AI. So as you said, some people think now that, okay, I can fix the algorithm and see for which type of data is good. But in the future, actually, we have been actually seeing some examples. So you can have a lot of data sets. In some cases, you have, and then you have a lot of algorithms. So now your design becomes more complicated. You need to choose now which data set is better, which algorithm is better, and increase the complexity. We have been working indeed on the problem of transfer learning for intrusion detection, where we have a very limited data in a target domain. Now we can have multiple source domains, data sets, and we can see that some are better than others. And so this may complicate even the design of the machine learning algorithm, right?
Yeah, it certainly can, and it's certainly a so one good thing has happened, Alyssa, recently, which is I think even academics realizing the importance of data as part of the whole machine learning model building, which is there are two aspects to it. There was a lot of focus on because benchmarks kept the data fixed, and everybody worked on beating down that race of 95%, 95.23%, whatever the number might be, and they drive a certain behavior. But I think there is more and more realization, many times coming from practical context, that when these models are designed, there is more to the model than a accuracy number. Like for example, how robust it is to changes. It can be very good in certain domain, but it can go down exactly, certainly a little bit. And to me, it is the combination of these two. But I would rather pivot on data because I would like to drive a certain behavior. Everybody is of this mindset of algorithm. I want to see a change in the mindset of people in terms of how important data is. And more, I think we also need to make sure we ask people to focus on making sure the data set is clean as well. It's not about just crawling the web and collecting a lot of data and ingesting it, because it can be biased, it can have issues. In the panel I'm going to talk about software, and if you just crawl the web for software, there's all kind of software. There's software with vulnerabilities, there's buggy software, and you're going to learn that. Actually, that's exactly what you're going to learn. So it has to be a highly curated data set as well.
I agree, and actually I get very annoyed when I read the papers on attacks, on data poisoning attacks, where they say, oh, we can crawl this web and get this data set which has some malicious input. I say, if you needed to use a model for a critical application, you don't go and just getting data sets on the web. But they write such papers. Then I say, I don't know. They must have a good curation processes where you can use AI actually to do those processes as well. But,
I couldn't agree more. Actually, I couldn't agree more.
Okay, so then I think there are other questions, because the next panel will be in 12:30, so we have actually still a little bit of time. If there are no questions, I just ask you a question. So AI has been used in a lot of domains application, but do you see some areas in which AI has not yet been used a lot and which should be used, where there is potential there?
That's actually a good question. That's certainly a good question. So I would say following. Let me answer it in two parts. AI, where we think it would have tremendous impact, actually, and that's where we started on, including IBM as well. I would say, we started on this as well. Healthcare. And of course, it should have tremendous application in healthcare. There's lots of data we should be able to collect, but it hasn't been as successful in healthcare. as we expected it will be. So the adoption has been slower. And interestingly, I'll just give an anecdote to this. My wife is a physician as well. And this is almost a discussion 7 years back, actually, when we started with Watson Health. And I was discussing this with her, and I was very naive, I would say, in many ways. So we were just discussing, hey, we are doing this Watson Health, and she says, okay, this sounds interesting. And I said, she said, it's going to be a hard process. It's not an easy problem. And I said, I think you're just saying this because it's going to take away your job. I almost said it jokingly, actually, to her. And she kind of, she's a little bit more humble, so she kept quiet a little bit. And, look, she's usually right, so over me. However, lo and behold, you take a look 5 to 7 years later, and yes, she was right that it is quite a complex problem. So I think I just wanted to take us down. I think we think sometimes that it should really be applicable in that area, and it is not, because of we underestimate the complexity of the processes that are involved, the human factor that is involved. It's a much more complex discipline. It's not an academic discipline only. There's a trust factor. When a physician shows up by your bed, there is a trust factor to it. And I think humans, we are a lot more than just kind of intelligence itself, like that brain. We are again, I think you know what I mean. Actually, deployment of AI is a complex task. It is a lot more than NeurIPS papers, actually. So I think, so that is the first part of my answer on, where we expect it to be applicable. It hasn't been that successful yet either. But I do believe, I think there are other areas, for example, and we haven't made much dent into this, sustainability, climate, and kind of renewable energy, and those areas where there is, I would say, lesser human factor involved and more innovation from a technology point of view needed. These are pressing problems for the world. And I do believe AI, it hasn't been applied as much, actually, as I believe it could be applied into those areas. So that's an area where I would say I would like to see a lot more progress. And I haven't seen it as much. Because the impact can be much wider there, and the problems are very pressing, and the human factors are lesser, because you're not dealing with as much like healthcare with the patient who is in kind of, it's not a life and death issue right away. Obviously it's a life and death issue for the humankind, but not an individual patient and so on. So that is one area I would say where we can make a lot more progress. But there are obviously some conferences in the area, but I think we can make a lot more progress, including, I would say, to like material discovery, and so on as well.
But for example, could we in the future, by combining, let's say, sensors, AI, even prevent pandemics, like the one we saw where we just could react, but even try to prevent it? This will require even monitor animals in the wild, but could we, one day hope that the AI could help there, for example?
Yeah, I think it's certainly gonna require sensors, monitoring, maybe even drones from just collecting data. Again, I think the issues of it can become tricky because the privacy comes into play. Yeah. And some countries are okay with it, other countries are not. It becomes a tricky topic because sensing and monitoring, when you are trying to do this in a public health scenario, as we are seeing even in vaccine rollout, which to a lot of extent should be no-brainer, but there are still a lot of issues in rolling something like that out when you have a solution even. So again, we should not minimize, and I've learned that lesson the hard way, as I just mentioned to you, the discussion with my wife. But I think we should not underestimate these challenges from a technological rollout point of view.
Okay, I think we at this point we can close the session. But I would like to thank a lot our speaker. It was really an exciting talk and a very interesting discussion. Thanks again.
Thank you. Appreciate for inviting me.
So I think now we have the break and the panel will start, I believe, in about 15 minutes.
Okay,
So,
I'll stop sharing actually here. So.
Yeah, also.